Hello Internet, welcome to another tutorial in the series of network analysis and synthesis. In today's tutorial we'll do an interesting numerical on Z parameters. We've been given a network which has some capacitances and inductances, and the values for those are given. As we all know, we need to transform this network into the Laplace domain, and by the end of this numerical we should be able to find out all these Z parameters, which are, by the way, Z11, Z12, Z21 and Z22, where we know that Z11 and Z22 are driving point impedance functions and Z12 and 21 are transfer impedance functions. So first things first, transforming this network is easy. If you've been watching my previous tutorials, we know how to transform inductance into S and capacitance into S domain. So I'll draw the transformed network. We'll need to redraw it. And this 1 farad will become 1 by S. Again, this will become 1 by S. This will become twice of S. And this will also become twice of S. Now please understand, this voltage that we have on port 1 will be represented as V1 of S. This will be now represented as V2 of S, and the currents are also I1S. Let's say this is I2S and this is I3S. Now for the sake of simplicity, I'll write the notations V1S and I1S as V1 I1 in the numerical, and we'll finally replace them towards the end. So this is one thing that I'm doing while solving this numerical to keep the things minimalist. So over here what we are implying to do is we shall apply Kirchhoff's voltage law on the three meshes to find out the values of V1 and V2, because we know the from the discussion of Z parameters, the governing equations from where we find these Z parameters are V1 used to be equivalent to Z11 I1 plus Z12 I2, and V2 used to be equivalent to Z21 I1 plus Z22 I2. So if you remember the discussion on Z parameters, the derivation of Z parameters, these two were the governing equations. We derived those equations from Ohm's law, and so if we are able to find out V1 and V2 from this network, then by inspection we'll find out the value of Z11, Z12 and consequently Z21 and Z22. So what we are trying to do here is, from analyzing the meshes in this network, we'll try to find out one equation for V1 and one equation for V2. So after comparing the equations, we'll figure out these Z parameters finally. So from mesh 1 we have V1 minus I1 into 1 upon S minus 2s I1 minus I3 is equivalent to 0. So in this mesh we are taking all the voltage drops in the entire loop. So this is V1, and the voltage drop across this capacitor is minus I1 1 upon S. If you want to label positive and negative signs, you could do that as well on the entire network. So this is equation number 1. So further consolidating, we get V1 is equivalent to I1 into 1 upon S plus twice of S, I1 minus twice of S, I3, which is equivalent to I1 1 upon S plus 2S minus 2S into I3. Now please understand, we are segregating terms with the currents, with respect to the currents, because we are segregating everything in S with I1 and then everything in S with I3. So this is the form that we'd like to keep for mesh 1, and similarly for mesh 2 we have V2 minus twice of S, I2 plus I3 is equivalent to 0. So this is our mesh 2, and in this mesh we just have one voltage at the output terminal and one element in the form of inductor. So the drop across inductor is given by this term, and V2 is this. Alright, now we can finally keep this equation in the form of twice of S into I2 plus twice of S into I3, because we can substitute this equation elsewhere in the numerical. And for mesh 3, which is the mesh in the center, we'll drive the equation that will become something like this. Now please understand, mesh 3 has 3 elements, and we need to specify voltage drops across all the 3 elements like this. So this is the voltage drop across capacitor, and this is the voltage drop across inductor, this is the voltage drop across inductor. So finally, from this equation, I'll skip a few steps for the sake of saving time. I need to find out the value of I3. So what you can do is you can find out the value of I3 from this equation. That will come out to be equivalent to this. Now the importance of finding the value of I3 from here is that we'll substitute this value of I3. Now if you look closely, we have found the equation V1 in terms of I1 and I3, and we found the equation for V2 in terms of I2 and I3. However, we need equation V1 in terms of I1 I2 and V2 also in terms of I1 I2. So that is why we'll find I3, which is in terms of I1 and I2, and we'll substitute it here and here, and we'll be left with I1 and I2 terms in both the equations, and then we'll compare them with the standard Z parameters equation, and we'll be able to find out all the parameters. So substituting the value of I3 in I'll say this is equation number 1 and this is equation number 2. I'll get V1 to be equivalent to 4s raised to the power 4 plus 6s square plus 1 upon I1 plus 4s cube upon 4s square plus 1 I2. Now, does it not resemble the first standard equation for Z parameters? Yes, it does. So we have V1 in terms of I1 and I2, and clearly the coefficient of I1 or the term glued to I1 is nothing but Z11, and the term glued to I2 is nothing but Z12. So from this equation, half of the question is solved. Two parameters are found. Z11 comes out to be equivalent to this term. I'll write the term again quickly. So this function is Z11 and Z12 becomes equivalent to this. And now substituting I3 in the second equation will give me V2. You simply need to substitute this complicated I3 value here and get the value of V2. And V2 becomes alright. Now please understand this equation also resembles exactly to the second standard equation of Z parameters, and from here we will find out the value of Z21 to be equivalent to 4s cube upon 4s square plus 1 and Z22 to be equivalent to 4s cube plus 2s upon 4s square plus 1. Now we already know that all the Z parameters are functions which have a numerator in as a polynomial of s and a denominator as a polynomial of s also. And once we know these parameters, we can investigate further and comment on the stability of the driving point functions or the transfer functions. We will be able to know whether these functions are feasible at all or not. But first, the first thing is to find out the values of these functions from a given network, and that is how we do that. So I hope the method of finding Z parameters from a network which is given in its standard form is clear, and I hope you liked the tutorial, and if you did, give it a thumbs up, and I'll appreciate all the support in terms of supporting the channel as subscribing, sharing and commenting. Thank you so much for watching the video. I'll see you in the next one. Goodbye.